lecture number 21, Kinetic Molecular Theory of Gases and then Real Gases. So we've been talking about these gases as sort of this nebulous thing where we have just these molecules that we're sort of ignoring in this thing that either has a pressure or a volume or whatnot. And we've sort of ignored what those gas molecules are doing. So in this lecture, we're actually going to focus primarily on the motion and the energy in those gas molecules and how that's related to those theories we've looked at before, some of those other laws that we have available. And then see what we're not talking about ideal gases. Remember, there's no ideal gases. So how do we correct the things we've done to take into account those non-ideal gases? So first, let's look at this kinetic molecular theory of gases. It's based on 3 postulates, which are listed here with some additional sort of assumptions. So the first is the gases are composed of molecules that are separated from each other by distances far greater than their own dimensions. Right? So molecules can be considered as points, and they can consist of negligible volume. So we sort of mentioned this before when we talked about this assumption made in the ideal gas law, that the volumes that we're talking about of the gases are so much bigger than the molecules themselves that we sort of ignore those. Right? We're considering them points. Postulate number 1. Postulate number 2 is that these gas molecules move randomly. So they move in random directions. But those directions are in straight lines. So it'll move in straight line in this direction until it hits something, and then it'll bounce off in a straight line. Right? And then all collisions that it has, we've talked about this before, again, are elastic. So it bounces and just changes direction. The energy that it accumulated in those changes, or by those interactions, doesn't change. So it maintains the amount of kinetic energy that it has. It just simply changes direction. The third postulate is that the gas molecules don't attract or repel each other. There's no interaction between those molecules. So again, this goes back to one of the assumptions we made in the ideal gas law, that those molecules don't attract or repel each other. There's no interactions. Again, we're just restating it here in our now reflecting the energy. Excuse me. And what this means is that the average kinetic energy, this number 4 here, isn't directly related to a postulate, but it's just sort of a result. The average kinetic energy of the molecule is proportional to the temperature of the gas in Kelvin. So 2 gases that have the same, are at the same temperature should have the same average kinetic energy. So there's a relationship of temperature. So that's proportional. So these are those first 3 of the postulates for the kinetic molecular theory. The 4th is sort of a result. But all of these are the assumptions we're making when we talk about this kinetic molecular theory. So now with this in mind, these sort of things, let's look back at all of those laws that we discussed earlier, the properties that we discussed earlier, and see how these are explained by this new theory. So first, let's talk about the compressibility of gases. Right? We said very beginning of the chapter that these gases are the most compressible, right? Which makes sense. If the distance between the gas molecules is so great, it's easy for them to be squeezed closer together. Right? We have that ability before they sort of make contact. So this idea that they're far apart is well within, or helps us explain this compressibility of gases. Let's look at Boyle's law. Boyle's law, if you remember, says that pressure is inversely proportional to volume. If we think about in this kinetic molecular theory, the pressure of a gas is directly related to how many collisions of gas molecules there are on the container. Right? The more collisions, or the higher those collisions are, the higher the pressure is going to be. So we can say that the pressure is directly proportional to the number of collisions that hit the wall of the container. And that collision rate is then directly proportional to the number density, or how many gas molecules we have per given volume. More gas molecules per volume, the more likely they are to hit the surface. More likely to hit the surface, the higher the rate is. The higher the rate is, the higher the pressure is going to be. And that density is, remember, inversely proportional to volume. The larger the volume, the fewer number of molecules we have within that volume. Fewer number of molecules we have, again, lower the pressure. So this kinetic molecular theory explains Boyle's law. Let's look at Charles' law. Remember, Charles' law said that the pressure or volume is directly proportional to temperature. So again, if we look at it in terms of pressure, the pressure again is a function of how many molecules collide at the wall. The collision rate is going to depend on how fast those molecules are moving. The faster they are moving, the more likely they are to hit the wall, or the quicker they are going to go from wall to wall. And the speed that they're moving, that average kinetic energy, is directly related to temperature. Right? So the higher the temperature, the faster molecules are going to move. Faster molecules that move, the more they're going to hit the wall. The more they hit the wall, the higher the pressure. Again, kinetic molecular theory explains Charles' law. Right? Look at Avogadro's law, the last one. Again, we talked about it in terms of volume and number of moles, but since volume and pressure are on the same side of the equation, we can do it to pressure. Right? The number, again, pressure is related to the number of collisions at the wall. Collision rate, just like in Boyle's law, is related to the number density, the number of molecules per unit volume. And that number density is directly proportional to the number of moles we have. So the more moles we put in the container, the greater chance those molecules are going to have to hit the wall. The more likely they are to hit the wall, the higher the pressure is going to be. So the pressure is going to be directly related or proportional to the number of moles. Right? And finally, the last rule we talked about was Dalton's law of partial pressures. So since the molecules don't react or interact with each other at all, it doesn't matter what type those two molecules are. It doesn't see them. Right? They're sort of unaffected by anything else. So the pressure exerted by one type is only related to its type hitting the wall. So if we separate those types, they're unrelated, so the total pressure is going to be related to the total number of collisions per type of gas molecule, or the total pressure is going to be the sum of the partial pressures. So because it doesn't matter, there's no interaction between those two different gas molecules, it doesn't matter that they're both there. Right? Each one sort of acts independently. So we can see this new theory of not really explaining the motion of the gas molecules can take into account all of those gas observations that we've made before. So let's go back to that last postulate, or that last sort of assumption there, that the temperature, the gas molecules at the same temperature are going to have the same kinetic energy. Right? So we can do this one of two things. Right? So it means that as we change temperature, the speed of molecules is going to change. So if we look in this top graph here, we look at nitrogen molecules at 100 Kelvin, 300 Kelvin, and 700 Kelvin. As the temperature increases, we see that the average speed increases. When we say average speed, we're talking about the midpoint, that peak of that curve. Right? It's an average, so not all molecules are going to be moving at that speed or that rate, but the average of them are, right? Sort of the middle point of the curve. And as that temperature increases, we see that the average speed increases. But what else we also notice is that the total number of molecules going at that speed is going to decrease because the peaks get wider. Right? So when we talk about this average speed or average kinetic energy, that's for the average. There's still a distribution there. Right? If we look at the second plot down here, we see that if we go from chlorine to nitrogen to helium, the heavier that molecule is, the slower it's going to go. It sort of makes sense, we should think, right? Chubby things tend to move slower than light things. Right? It works in molecules, it works typically in people too. Right? So the heavier something is, the lower that average speed is going to be. Before we talked about the average kinetic energy, here we're talking about what we call the root mean square speed. Right? So down here, the root mean square speed is equal to the square root of 3 RT divided by the molar mass. So in this case, we're using just the 1m for molar mass, but that's the molar mass. Right? The 3 comes about because there's 3 different directions it can move. So there's 3 sort of rotations that it can have. And then we have the gas constant and the temperature. So again, this is related to the kinetic energy is going to be related to the speed. So, but in general, as we increase the temperature, the root mean square speed and the kinetic energy will increase. For any given molecule, because of their different masses, if they're at the same temperature, the heavier one is going to move slower in terms of speed. The kinetic energy, as we saw before, should be the same, but the root mean square speed is going to be lower. So we're going to take advantage of this root mean square speed by looking at gas diffusion. So gas diffusion is the gradual mixing of gas molecules with molecules of another type by virtue of these kinetic properties. So this random movement of those molecules is going to allow 2 different gas molecules to mix together. Right? And the way that they mix is related to what we call Graham's law of diffusion. That under the same condition in temperature and pressure, the rates of diffusion, how quickly they spread across a room, is going to be inversely proportional to the square root of their molar masses. So something that is heavy is going to diffuse slower than something that is light. We'll talk about effusion, which is, instead of going across a distance, it's the speed at which a molecule will exit an opening. Right? It's the same basic process, it's just sort of our frame of reference that differs. So if we look at this picture down here, we see ammonia is in one bottle and hydrochloric acid is in the other. Right? So where they are mixing, we see this gas cloud form, right, to form the ammonium chloride solid. Right? So based on this law, Graham's law of diffusion, we can predict, even though you can't maybe read it, which one is HCl, which one is ammonia. Right? If we look at their molar masses, ammonia has a molar mass of about 17. Hydrochloric acid has a molar mass of about 36.5. So according to the Graham's law of diffusion, the heavier one is going to move slower. So we can see that this one on this side is the hydrochloric acid, because the gas cloud is here. So it is not, those molecules are moving slower, they're not traveling as far because they're heavier. We can then calculate that using this equation here, that the rate of one molecule divided by the rate of the other is equal to the square root of the molar mass of the second one divided by the molar mass of the first. And we will do these types of calculations in class. Okay. Excuse me. So we saw that this kinetic molecular theory of gases is very similar to the ideal gas law. So let's review then those assumptions to ideal gas. So we're going to finish out this chapter talking about when these assumptions are no longer valid, and then how do we correct for those. Right? So our 2 assumptions, remember, were that gas molecules have negligible volume, they're points compared to the container, and that the gas molecules don't interact. Right? So we're going to see the biggest deviations where these two, one of these two or both of them, become invalid. Right? The assumptions are no longer true. Right? Which would be when we bring the molecules close together. Right? And the 2 things that can cause molecules to come close together are high pressure, and we're squeezing those molecules down so that they're close together, or a small volume. Right? Or, I guess the other way is if we just pack in a large number of moles. Right? Anytime we get molecules to end up being very close together, we're going to see a big deviation from ideal behavior. Right? That deviation you can see here is for all gases in this chart. But what this means is that we then have to correct the pressure and the volume for these non-ideality of real gases. And we use that doing the van der Waals equation for a non-ideal gas. And the van der Waals equation is listed here. What we're doing is we're correcting the pressure for the fact that the molecules have volume and interact. Right? So we're taking some factor times the number of moles squared divided by the volume squared, and then the B, or the volume, we're correcting by taking the number of moles times some other value. Right? A and B in this equation have to be given to you. They're listed in this table here, and that's a small portion of gas molecules. But so if you're given these values, then you have to correct for them using this non-ideal gas equation. Don't necessarily say you have to memorize this equation, because most of the time the gases that we're going to work with, we're going to assume to be ideal.
Dad, I done did it.